Now, we didn't have to wait until the Apollo mission to find out that the Earth indeed has the shape of the sphere. People have figured it out thousands of years ago. In fact, a 4th century BC, Greek philosopher Aristotle was the first one, as far as we know, to actually figure out that we'll live on the surface of the sphere based on observations. So Aristotle was probably the most influential philosopher of natural world in antiquity, and he used observations to deduce that the Earth on which we live has the shape of the sphere. He also argued that the Earth must be the center of the universe, and he had some general philosophical principles to argue that, but also from observations that if you jump up, you always come down. It seems that everything thrown up on the surface of the Earth is falling down. It looks as if everything is being attracted to the Earth. But his observations regarding the shape of the Earth were actually much more sound than that, because his argument about things falling down on the surface of the Earth are a consequence of the force of gravity exerted by the Earth, and at his time that was not really well understood. So the arguments that Aristotle used to conclude that the Earth is spherical are as follows. If one travels south, say from point A further down to point B, one starts seeing new stars that were not observable before. And an observer at point A on the surface of the Earth, he can see everything above his horizon, the plane underneath his feet. So when the observer is at A, he can see this top star because it is above his horizon, but he cannot see the star below because it is below his horizon. He cannot see anything below his horizon. So at A, he can see only this top star here. But if he moves south, if he goes from point A to point B, then as he shifts his position, the horizon also changes. So now the horizon, this plane underneath his feet, is as indicated. And now at point B, he can see not only the above star that he was able to see from point A, but he can also see the second star that he could not see from point A, because now both stars are above his horizon. So just this simple observation that as one travels south, one starts seeing new stars, tells us that the observer is moving on the surface of the sphere. The second observation that he used to conclude that the Earth must have spherical shape is that during lunar eclipse, the Earth's shadow is always circular. I mean, they realized that basically during the lunar eclipse, the Earth casts its shadow above the moon, and this shaded area here is Earth's shadow, right? The sun is shining behind us, and the Earth is casting the shadow. And then as the moon is revolving around the Earth, it will eventually move into the Earth's shadow. And one can see that regardless of the stage of the eclipse, the shadow is always part of the circle. That can only be if the Earth has a spherical shape. Only then we can have the shadow that Earth casts on the moon be a part of the circle. You can say, well, if I have a disk, like this coin here, right, it will also cast a circular shadow. But not always. And you can actually experiment with the flashlight and the coin. If you shine the light at different angles, the shadow of this coin will not always be circular, right? It will be, in general, some elongated oval. Only a perfect sphere will cast a circular shadow regardless of the angle at which the light is illuminating the sphere. Okay, so this was the second observation that he used to conclude that the Earth must have spherical shape. And the third one that I guess all of us are familiar with, if you stand on the shore of a lake or a sea or the ocean and observe boats that are approaching the shore, when the boats are far away, you can only see the tip of the mast. But as the boats start approaching the shore, as they get closer, you start seeing more and more of the boat. And eventually, if the ship is close enough, you can see the entire boat. Again, this observation is the consequence of the fact that the Earth is spherical, right? So if a boat is very far away, its full view is obstructed by the curvature of the Earth. And only when it approaches close enough, we can see the entire boat. At relatively short distances, we can ignore the curvature of the Earth. We can approximate the surface with the flat plane.